In this video, we're looking at sign diagrams of f dash of x. So first step for finding a sign diagram of f dash is to do the derivative. So we've got this function x squared takes 6x. As a reminder for how to do the derivative, the 2 comes out the front of x squared, and the new power drops by 1. So it's just x to the power of 1, or just x on its own. And then we're going to take away, and 6x just becomes 6, like that. Okay, now that we've got the derivative, we need to find critical points. So it's f dash of x is 0 or it's undefined. We're not going to do it in this video, the undefined one, but we do have a point where f dash of x equals 0. So we're trying to solve that. So it's 2x take 6 is the derivative. We'd like that to equal 0. So that would tell me that 2x was 6, or in other words, x would be 6 over 2, or 3. Okay. Next step to making a sign diagram is we have to draw the sign diagram itself. So the sign diagram looks like this. You put x there and you put f dash of x there. Right now we're only going to do sign diagrams of f dash of x, but whatever you're drawing a sign diagram of, you put there. Okay, so we got to put this point x is 3 on there, and then we have to plug in some numbers to the left and the right of 3. So for example, f dash of x is 2x take 6. So if we look at f dash of, let's pick a number bigger than 3, like 5 over here, it'll end up being 2 times 5 take 6. And all I care is that that is positive. I mean, the answer is 4, but it's a positive number. So we're going to put a plus over here where the 5 was. And then we've got to pick a number smaller than 3. So maybe 0. So that's 2 times 0 take 6. And all that I care about is the answer is negative there. So minus there. Okay. Now that we've got that sign diagram, we can find where f of x is increasing and decreasing. So it is increasing wherever there was a plus on our sign diagram. So that's for x is greater than or equal to 3. And it is decreasing wherever x is smaller than or equal to 3. Note that it is both increasing and decreasing at the point 3. And if we look at a picture of the function, here's 3, or x is 3. You can see that if we're walking along this function, we're walking uphill after 3. Whereas if we were before 3, we're walking downhill. At that point, exactly at 3, we're sort of walking both uphill and downhill. So we say it's both increasing and decreasing. You're always walking to the right when you do this. If you wanted to use more precise terminology, you could use strictly increasing. That would be where x is strictly bigger than 3. And strictly decreasing would be where x is smaller than 3. So sort of all the definitions here. Increasing would be that the derivative is positive or 0. This would be that it's less than or equal to 0. Strictly increasing would be that the derivative was strictly bigger than 0, or the derivative was strictly less than 0. So those are sort of the definitions there. And last, we need to classify all stationary points. So at x equals 3. Now the stationary points, we sort of got 3 different types. The 3 types look like this, and you can tell from the sign diagram. Our sign diagram goes minus then plus, so that's a local minimum. So we have a local min at, now x would be 3, and to get the y coordinate, we can plug this back into the function. So our function itself was x squared take 6x. So 3 squared take 6 lots of 3. That would be our function when x is 3. So that's 9 take 18. So that's minus 9. So there we go. And you can see that on this graph, this point here, 3 minus 9 is a local minimum. And anything to the right here is increasing, and anything to the left is decreasing, because we'd be going downhill if we're walking there. Cool. Now, the reason we call it a local minimum is because sometimes these functions can go back down afterwards, and then we'd actually have a lower minimum point there. So it's only ever locally. If you zoom in, that's a minimum point. Okay. Now, that's how you do it purely algebraically, but realistically with most functions, you're looking at a picture because you've graphed it on your calculator, and you can use that to influence your answers and get it a bit quicker. So I'm going to show you sort of the actual way you're going to do this and almost like cheese your answers a little bit. You've got to get the derivative first still. So 2 times 5 out the front is 10, and the new power is 4. Then x to the 4 becomes 4x cubed, and 4x cubed becomes minus 4 times 3 is 12, x squared. Now we want to get our critical points. So these would be f dash of x equals 0, or in other words, all that stuff up there equals 0. Now you can do the whole thing where you factor out the x squared and solve this as a quadratic. And I'd encourage you to try that if you want some practice. But more often than not, you've got to use technology to solve this. So we're just going to go into equation mode, F2 for polynomial solver, degree 4, because we've got x to the power of 4 as our biggest power, at 10x4, 4x cubed, minus 12x squared, 0x, and 0 is a constant. Solve that, and we'll get some answers. 0.9135. And our other solution was minus 1.31. And let's go 3 significant figures for everything. There we go. Now we can actually draw our sign diagram. So to get our sign diagram of the derivative, I'm going to put those 3 numbers on there. So that would be 0. Try and keep everything on a sensible scale. 0.914 minus 1.31. And you can actually use the slope of your function. So here we're going uphill. So I'm going to put a plus there on the sign diagram. Then at this point, which looks to be minus 1.31, that's the flat bit, so that we've labeled that on our sign diagram. And then we're going downhill, so I'm going to put a minus after that. Now it does go flat at 0 again, but it doesn't go back up again. It still goes downhill after that. And then it goes flat, and then it goes uphill. So your next bit on the sign diagram will be a minus and then a plus, just like that. Okay. So we need to say where it's increasing and decreasing. So it is increasing for x is less than minus 1.31 and x is greater than 0.914. And it's decreasing when x is in between those two numbers. So minus 1.31 is less than x is minus 0.914. So pretty much increasing are all the uphill bits and decreasing is all the downhill bits. Now we need to find and classify all stationary points of our function. All right, so we're just going to go into our calculator on graph mode. We're going to go to x to the power of 5 plus x to the 4. Take 4x cubed. Now I'm graphing this just to get the y values really quickly. So there it is. We may want to change our window. I might just hit standard and we'll get a nice picture of that. So if we go gsolve max, it'll find that first max we found, so minus 1.31 on the x and 4.22. So that's one of our points. This is a local maximum. And you can also tell from it being plus minus on the sign diagram. So it goes sort of uphill, then downhill. That would be a maximum. And you can also tell from the graph itself. So we've got a local max there. It's the top of the hill. Okay. We're going to have 2 more stationary points. So these are our critical points here. 0.914 and 0. So we'll just see if we can get those ones. So you could have got that local max with the maximum button, or you can trace and then go minus 1.31, up to you how you want to do it. For the 0 point, you'll notice that the calculator does have a max and a min button, but it can't find these flat bits that look like this very easily. This is the stationary point of inflection. It's the weird one. Stationary point of inflection. And the only good way to find the y coordinate is to just plug the x coordinate in. So I'm just going to go trace and then type 0, y is 0. And for the last one, that looks to be a local minimum on the graph. So we're just going to go gsolve min and we'll find that other point. So 0.914 and minus 1.08. So you can see here that we can sort of use the calculator to get a lot of this working out for free. So this is a calculator version, and the bit at the top is if you wanted to do it purely algebraically. But more often than not, you're using your calculator to help you.